You guys can still hear me, right?
Professor Dixon, the time is, I think that it is done as per the schedule we are, so you may start. We are waiting for your talk to start.
Okay.
Yes.
Well, again, just thanks everyone for the invitation to have me come and speak today. This area that I'm going to be talking about is one that we've been focused on the last, I would say, 5 or 6 years. I've spent my entire career focused on adaptive control for nonlinear systems and using Lyapunov-based analysis techniques to understand how to design the adaptation laws and show stability of the developed adaptive controllers. So we've used a variety, gosh, all the different types of adaptive controllers one can imagine, including neural networks. And we were using shallow neural networks for many years. And with the emergence of deep learning, we obviously were very interested in, okay, what does that mean for adaptive control methods? And as you'll see in a moment, there's some technical obstacles that had prevented the community from moving forward with using deep learning in a way that one could use stability analysis methods like Lyapunov methods to help design the adaptation laws. And we were able to overcome that a few years ago, and that launched us down this really fun journey. And that's what I wanted to share with you guys today. And so one of the outcomes of this journey is that we're able to do real-time deep learning, so and even without data. And so that's why I titled the presentation Real-Time Deep Learning. And as we go through the presentation, hope to clarify more what that means. So first of all, I get asked sometimes, well, why deep learning? Strictly speaking, from a stability analysis perspective, you're not able to show that you get improved results by using deep learning from a theoretical perspective, but there's a preponderance of evidence that's been published in a variety of different communities that show that the depth of the neural network provides improved function approximation properties. And so this is a video that was done. And you'll notice my name is not on here at all. This was a group of people in the U.S. Air Force that University of California, Santa Cruz, that implemented a number of control methods, including one of ours. And I think it motivates why one would want to do deep learning. So I'm just going to pause it here for a second and explain what you see in the video. So this is a top-down view of a quadcopter, and attached to one of the legs of the quadcopter, you can kind of see it hanging off here, is a partially filled water bottle. And you have a fan that's blowing a significant airflow across the quadcopter, and it's swinging this water bottle underneath the bottom of the quadcopter that's providing a continuous disturbance. That disturbance would be hard to model, and so that motivates why you would want to use some kind of adaptive or robust control methods to compensate for that. And so one method that you that you might be interested in using is a PID controller. This is, one of the baseline kind of bedrock controllers that someone would maybe want to use, and you'll see its performance when I run the video again. Another controller you might be interested in using is a model reference adaptive controller, and that's going to be shown here. And then there was, I acknowledge it as probably the first example of a deep learning controller that used a stability analysis to design the adaptation laws. It was for a linear system, and they only updated the outer layer weights of the neural network. And then the inner layer weights were trained offline and held constant. And then this was a controller that we had developed, and this was developed for nonlinear systems, but also in the similar spirit as this controller by Girish Chowdhury, which only updated the outer layer weights. And so if I continue to play the video, and so the goal is for the quadcopter to track this blue circle. And once they get going, what you'll see is that the PID does the worst. It's not very good at all. Model reference controller is a little better, but still pretty terrible. The deep model reference adaptive controller for linear systems does better than the others. And then this was our deep adaptive controller for nonlinear systems. It's still not doing great, but it's doing better than the other methods here. And again, I just want to remind you that in this controller, they implemented a version that only the outer layer weights of the deep neural network were being updated in real time. This is another experiment that we did, and here again you see a quadcopter. It's got a partially filled water bottle that's dragging, and here it changes altitude. So when it's down here, it flies low and drags the water bottle. So there's like a friction and dragging force that's there. It receives a disturbance from this fan that's blowing left and right, and then this fan that's blowing in this direction. And when it gets down towards this end, it's flying with a higher altitude, so the water bottle is swinging around without dragging on the floor. So it's a different type of disturbance. This result that you see here is one that we've developed where all of the weights of the deep neural network are being updated in real time. And even for this, these kind of disturbances where you've got this water bottle sloshing around underneath it, especially when it gets in front of the fans, and then it even gets drug on the ground, it's able to compensate for those disturbances. So those videos, I hope, tend to motivate the fact that with deep learning, we may be able to do better compensation for uncertainties, and in particular uncertainties that would be very hard to model using first principles. For example, this sloshing around of the water bottle, or the water bottle as it drags on the ground, and the aerodynamic effects that are blowing the water bottle and then causing the movement of the quadcopter. But if you were to review what is the current state of the art in deep learning, which has been promoted mostly from machine intelligence, AI, deep learning kind of community, is that they're very good at pattern matching, but they haven't really been applied for feedback control. And some of the things that are challenges is that the way that deep learning is typically implemented is that it requires massive amounts of training data. And this training data is used to adjust the weights of a neural network offline. This can take minutes, hours, days, weeks. It takes high performance computing to be able to do that, typically. And at the end of the day, you've trained the weights of the neural network on this closed data set. And maybe it represents the environment that your system would be operating in, or maybe it doesn't. And regardless, there's no, the way, so the way that these data sets are used to adjust the weights of the neural network is that they use a numerical optimization method, which doesn't have any guarantee of convergence or stability. And when these neural networks are trained and then used in a control system, they're implemented in an online way. And what I mean by that is the training has been done offline from the closed data set, and then the weights are fixed. And then when the control system is then implemented, you essentially have a fixed static estimate, feed-forward estimate of your dynamics or your system, but you're not learning anymore. The learning has been cut off because you're not doing, there's no method, there's no rule, there's no approach to how to adjust the weights in real time. And so this is where this was motivation for us to move forward. And we ask questions of, can we use Lyapunov-based methods to develop analytical update laws? And the opportunity there would be that if we implemented these adaptation laws within the deep learning architecture, and these adaptation laws are derived from the stability analysis, then we have a stability analysis that gives some indication of the performance, the robustness, the trustworthiness of the adaptation law. Also, because these are analytical update laws derived from the stability analysis, then we can implement them in real time. I mean, there is a computational cost, that's true, but we've been able to implement these real-time deep learning methods on quadcopters, on mobile robots, on all kinds of different systems. With GPUs, NVIDIA processors, but not high performance computing, which would typically be used for offline training. And this doesn't mean that we can't exploit the vast community and results that have been done for offline learning. So if one had the opportunity to have data and have the time and resources to be able to do offline learning, well, that's fantastic. That just provides an initial condition for the kinds of work that I'm talking about today. So you would do that if you wanted to and had the capability of doing that. But instead of just freezing your weights and turning off the learning during real-time execution, now we are going to be able to continuously update those weights during real-time execution. And because of that, that enables us to have these kind of stability guarantees and improved performance as the system executes. So I just want to review neural networks, the basic structures of neural networks for everybody. So if you have some function, we'll consider it a Lipschitz continuous function. Then the universal function approximation property says that you can approximate this function up to some reconstruction error epsilon. And this could be an example of a shallow neural network where you have one set of outer layer weights and then one set of inner layer weights. And people have been able to design analytical update laws using Lyapunov-based stability analysis methods, for example, for these kind of shallow neural networks since the 80s, early to mid 80s. But with deep architectures, the problem is in this middle equation, you see that there's weights embedded inside of nonlinearities, and those embedded nonlinearities have uncertain weights embedded within them, and also embedded in nonlinearities. And it's just this continuous embedding of an uncertainty inside of a nonlinearity that can't be factored out. And so that's been a technical issue that has impeded the ability of people to develop adaptation laws for these kind of deep architectures. And it's well known by different communities that one way that you can express the deep architecture is through these composition functions. And so here you have a set of weights multiplied by a basis function that will be composed with another set of weights and another basis function for arbitrarily deep architectures. But it wasn't until one of my students, Omkar Patil, was able to realize that you can exploit that compositional structure of this deep architecture. And then he was able to figure out, and this is a picture of him on graduation day. He was able to figure out how you could exploit that compositional structure in a stability analysis to be able to derive analytical update laws for all of these embedded weights within the architecture. And that was the spark that really led my entire group down this journey. And so now we can exploit this compositional structure to write this recursive representation and design layer by layer adaptation update laws for an arbitrarily deep neural network. And so this was a major discovery for us, and we spent a lot of time and many pages of math deriving the analytical update laws, exploiting this compositional structure. And in the end of that, we developed this adaptation law, which is in the middle of your screen. And for those of you who are familiar with adaptive control, this adaptation law looks very familiar to you. This is the same gradient-based adaptation law that people have been using since the early 80s for all kinds of adaptive update laws, including for shallow neural networks. And when we got to this conclusion, this is what the stability analysis told us the adaptation law would need to be. I was initially a bit disappointed because we did all of this work. We felt like we made this major breakthrough, and all we did is reinvent the standard gradient adaptation law that people have been using for multiple decades. But then it dawned on me that the beauty is in the simplicity. And this middle term, this phi prime, this is a Jacobian term that would be typical in adaptation laws. But when I paid more attention to what this Jacobian term looked like, now this is where the depth of the architecture comes into play. And so here you see these partial derivatives with respect to all of the weights within the deep architecture. And now you can see here, now this is just some notation. This is a right product, matrix product, and then a Conacher product. But this structure allows us to capture the arbitrary depth of the neural network. And what I realized is that if one were to develop an adaptation law for an arbitrarily deep neural network, then if you were to collapse that arbitrarily deep neural network down to a shallow neural network, then it should collapse back down to the adaptation law that people have been using for shallow neural networks. And in fact, that's exactly what this is saying. If you were to collapse this arbitrarily deep neural network, then this gradient, this Jacobian, would be exactly the Jacobian for a shallow neural network. And so what this result really then is a generalization of adaptation laws for shallow neural networks through arbitrarily deep neural networks. And so that was a really interesting outcome that we were really excited about. But this is a feed-forward neural network. There are issues involved with overfitting, along with a number of other issues that come up with the depth of the neural network. And people in the AI community, machine learning community, have developed different architectures to try to address different problems. And so one of the problems with this feed-forward arbitrarily deep neural network is a vanishing gradient. And so one of the techniques that's been developed in the machine learning community is to develop residual neural networks. And residual neural networks are graphically depicted in the upper right, where you simply have these shortcut connections so that the influence by, say, this layer of the neural network isn't just filtered by subsequent layers. You can push it forward in the architecture so that it has an increased influence, which would philosophically prevent the gradient terms from these elements from vanishing. And so, you know, this different picture has different mathematics. You can see here that because of the shortcut connection, you have a different algebraic equation here. And so then we add, and each of these phi blocks here would be a fully connected deep neural network. And so then we went back to the Lyapunov-based stability analysis, and we said, okay, well, can we again write this in a recursive representation? And the answer is yes. And can we develop adaptation laws that that also represent this residual network architecture? And again, we derived the same adaptation law with this Jacobian, this phi prime. But when you dig into the phi prime a little bit in more detail, here you see these capital gammas are just the matrix products of the that captures the compositional nature of the deep neural networks. But then you see that the algebraic structure of the residual network is captured at this layer. And so what this means is that we can represent any of these block diagram residual network architectures through this same kind of strategy where these adaptation laws are derived from the stability analysis that gives you this analytical update law, which can be implemented in real time, even without any prior data. And so we are able to show that the errors in the system asymptotically converge. We have some gain conditions that have to be satisfied. This just shows a little bit of insight into the Lyapunov-based analysis that we are able to use to show error convergence for this system. For those of you who are familiar maybe with Lyapunov-based analysis, I thought you may appreciate this, and I wanted to drive home the fact that the adaptation laws that we're deriving are dictated to us. You can see here, if I were to take the derivative of theta tilde, I get a negative theta hat dot, and so this is the negative term, and then this is the adaptation law, the theta hat dot, and then these terms are used to cancel uncertain terms in the residual dynamics. And so it's these uncertain dynamics that are present in the stability analysis, which are being used to define what the adaptation laws need to be in order to cancel those terms out. Hence, we name these kind of deep learning architectures Lyapunov-based deep learning, or LB-DNN. So we did a simulation, a comparative simulation between a fully connected deep neural network and a residual network that I just showed you, that's supposed to combat this vanishing gradient problem. To the right, you can see all the adaptation weights within the deep architecture, and they're somewhat converging to some steady state value. And you can see that very quickly we get significantly improved tracking error performance by our residual network. And F tilde is the function approximation of the uncertain dynamics F within our system. And you can also see that we're approximating the function better with the residual network instead of the fully connected deep neural network. So then we started to look at other innovations that have been developed within the machine learning community. And one of those innovations is physics-informed neural networks. And so to just kind of briefly explain the difference here is that traditionally, so this is an Euler-Lagrange dynamic system, which represents many practical electromechanical systems. And if you have uncertainties within these dynamics, one way that you could approach this is to just approximate all of these uncertainties with one large-scale neural network, shallow or deep, and you would get a result. But if you understand something about the structure, so the first principles model of the dynamics, even though there may be uncertainties within these dynamics or other dynamics which are hard to capture, then one way to implement a physics-informed neural network is to exploit this knowledge or some level of knowledge about the physics to craft how we would adjust different neural networks. And so, for example, I know my inertia matrix is only a function of the position, whereas my centripetal Coriolis matrix is a function of the position and the velocity. And my gravity matrix would be just a function of the position, and my friction matrix, depending on how you want to model friction, is a function of the velocity. And so we develop different approximations. First of all, we have to deal with the fact that some of these are vectors and some of these are matrices, and vectorize some of the matrices in order to put them in the proper dimensions to do the learning architectures for them. And then we set up individual neural networks for each of these terms in the dynamics. And and then not only are different terms of the dynamics functions of different states, but as we manipulate the Euler-Lagrange dynamics in our stability result, I mean, here you can see the inertia matrix is multiplied by acceleration, generalized acceleration, and the centripetal Coriolis would be multiplied by generalized velocity. And so then the structure, the dynamics that we would be approximating are slightly different. And if we have this insight into the dynamics, then we can exploit that and then develop unique adaptation laws. So for our inertial matrix, for example, this inertia matrix times the desired acceleration, and then this feedback term could be approximated in this way. And then these terms with the centripetal Coriolis could be represented this way. And then based on those representations, we can develop unique adaptation laws where you can see that some of the structure of the physics is coming into play into those adaptation laws, and the friction and gravity adaptation laws are pretty similar, but there is a difference in our inertia and centripetal Coriolis terms. And so you can see that we divided each of these terms up, and they're multiplied by different things within our controller. And when we implement those kinds of when we exploit that kind of knowledge of the architecture, then we're able to again get improved performance compared to a deep neural network, which would have just approximated all of the dynamics just in one kind of lump sum. And so this is not a surprising result. It just means that if we have some extra knowledge about the system, then we can encode that extra knowledge and yield improved adaptation and improved performance. And we're continuing to develop those efforts. If you're familiar with composite adaptation, we have developed a predictive error that's similar to traditional composite adaptive control. And this allows us to compare the actual torque with the estimated torque or control input for the system. And that allows us to encode additional dynamics in the adaptation law. And so we have some emerging results that are promising there. And we're also extending that work for systems described by partial differential equations as well, which is where really this work in the machine learning community originated, was in examining systems with partial differential equations. And so we're excited to also get to that state with that work. So everything that I've showed you to date has been feed-forward neural network, fully connected feed-forward neural network as depicted in this image to the right. And these kind of structures are okay for static systems where you're not looking at time evolution, but there have been these architectures that have been developed called recurrent neural networks, and these neural networks build in a memory loop, and these memory loops allow us to capture the temporal dynamic behavior of an uncertain function instead of just a static function of the state, for example. One of the and so we developed recurrent neural networks and did some work there, but recurrent neural networks, which could be represented by this block to the left, emerged into what's called long short-term memory neural networks in the machine learning community, or LSTMs as they're typically referred to. And then there's even more recent developments past LSTM called transformers. We also have emerging results related to transformers, but I thought today I would go through and describe the LSTM behavior and how it can design Lyapunov-based adaptation laws for the LSTM architecture. And so the LSTM architecture is this recurrent neural network, but it has these input, output, forget gate, and a hidden state that allow us to regulate the flow of information within the individual cell. And this is why these have been motivated within the machine learning community, because the ability to regulate the information flow through this cell allows us to capture the long-term effects in the adaptation. And so to explain some of this, again, let me refer to Euler-Lagrange dynamic system. And I want the actual states of the system to track a desired trajectory, QD, it varies in time. And then I'm going to relate this through a filter, R. And there are theorems that exist that if R is bounded, then E is bounded. If R goes to 0, E goes to 0. So then I can, this filter just allows me to, so low pass filter, it just allows me to look at the dynamic system at the R dynamics in a simpler way than looking at the second order dynamics. And I can compensate for some of these uncertainties in the Lyapunov analysis. They just naturally take care of themselves through certain properties. But then we lump a lot of the uncertainties, like the inertia matrix, the centripetal Coriolis, multiplied by these different terms, the friction of the system and gravity of the system. We lump all those things into this unknown function G. And then our goal is to use the LSTM model to approximate this function G. And so although this structure that dictates how the information flows through the cell is desired, it also complicates the dynamics, the information. There's an information dynamic that's in place that one has to account for. And so you have cell state dynamics, you have hidden state dynamics, and these dynamics get captured in this way, where you'll see the weights of the forget state, weights of the input state, weights of the cell state, weights of the output state that are captured within these uncertainties. And all these weights are uncertain terms. The cell also has these internal memory loops that can be obtained by integrating. So on the hidden state and on the cell state, you can integrate these differential equations and you can get these memory loops. And that's the whole point of the LSTM, is to embed that temporal memory within the system. And so then we can develop our control input. So we have some feedback terms, and then we have our feed forward estimate that's for the LSTM. And again, this is a Lyapunov-based LSTM, meaning that we're going to use the Lyapunov-based stability analysis to dictate to us the structure of the adaptation laws. So we develop estimates for our cell state, and we develop estimates for the hidden state. And within these estimates, you see that there are estimates for the forget state, weight estimates, output state, input state, and cell state weight estimates. And so we need to develop adaptation laws for those terms. Those you can see here. And again, the structure, the analytical structure of these terms are dictated to us from the stability analysis. So it's not just a numerical optimization routine based on offline data. It's something that's discover through the stability analysis, and then we get these analytical forms, and these are projection operators that enable us to do the real-time online learning. So in this case, we were able to get exponential convergence to a residual error, and that error can be made arbitrarily small. So then we started to look, okay, we've been able to apply this Lyapunov based, we've been able to exploit the compositional structure to develop this recursive architecture that has allowed us to design analytical update laws for these different LSTM, RNNs, feed-forward neural networks, residual neural networks. And so then we've continued to look at, well, what other kind of architectures are motivated and beneficial? And very recently, we've been working on graphical neural networks and CAN neural networks, or Kolmogorov-Arnold networks. Graphical neural networks, I'll go into a little bit more detail in the next few slides as we kind of wrap up a little bit. And then I don't have results that I'm going to show today, although we have some recent results that are coming out using this CAN architecture. And the difference between all of the things that I've been showing you are multi-layer perceptrons, where and that means that you have an activation function which is known, and then the weights that are multiplied by the activation functions are the uncertainties in the system. And you have a certain type of universal function approximation property for those multi-layer perceptrons. With the CAN networks, you don't know the activation functions, and you are basically learning on a grid through a B-spline approximation the different activation functions. And these kind of networks are motivated because as you learn the activation functions on the grid, it gives you some improved interpretability of the learning process. And so this is an exciting new development and new area where there's a lot of open problems to be explored. So going back to the graphical neural networks, and this is probably covered for you, but it says if you're a Google Maps user, then you're a GNN enjoyer, meaning that the underlying engine underneath Google Maps is a graphical neural network. And so the way Google Maps works is that if you wanted to get from A to B, this is a pathway that's then segmented, and each of those segments are given some type of cost. So to go from across this cell, yeah, there's 4 stoplights there, so it's going to cost you a certain amount of time. There's going to be a certain cost to go through that cell. Or this is just an interstate, and so you can move very fast through this cell. And so then you can take these cells and you can represent them by a graph. And then due to the graphical architecture and the cost to go from node to node, then you can do an optimization, and that's what Google does, is an optimization through this graph to determine the best way to get from A to B. And so that's for a static known road architecture with static infrastructure. And so while that's a great motivating example, we want to look at things like quadcopters carrying suspended water bottles that are being pushed around from wind currents. And not just one, but a network of quadcopters that are tasked with a mission, and maybe we don't know the graphical architecture. Maybe we have to discover the connections within the graph. Maybe we don't know the interactions among the agents because of different environmental disturbances that may be happening. And so those are some things that graphical neural networks can help us achieve. So if I were to look at a graph, and I were to look at a certain node, say I'll look at node 2, then I can see that node 2 has inputs from this node 3 and node 1. And node 3 is getting inputs from node 4 and node 5. And also it's getting inputs eventually back from node 2 as well. So here is node 2, node 4, node 5. And so you see that there's like a circular architecture, and this also represents a delay in the network. Also, node 1, which is an input to node 2, is getting inputs from node 2 and from node 6. And so we can encode that, we can encode this information flow within the network as a graphical neural network and attach that with a traditional feed-forward neural network, and express this for each of these nodes, and that creates this deep graphical neural network. There are some things that we have to pay attention to, though, and that's how the graphs are connected, because each of these graphs are all isomorphic. So they look, even though they're in different positions, the connections remain the same. And these are different permutations that express different graphs. And so an open problem is, how can you in polynomial time develop or to determine whether or not two graphs are isomorphic? And so there's questions on how you can test for a graph is isomorphic or not. And so there are some ad hoc tests, the WL test, for example, and this is a color test. And so if you have a graph that's represented by this left-hand side, then you can look at the connection. So if I look at this leftmost node on the pentagram, I see that there are 3 nodes that enter into this. And so I give that a score of 3. Whereas the top node is only getting inputs from 2 neighbors. So that gets a score of 2. Then if I were to look at this again, then this architecture is getting inputs from a 3 and a 2 and a 2. And so that would be, if you sum those terms up, then that would be a 7. And likewise for the 2, it's getting inputs from 2 3s, so that would sum to a 6. And then you can assign different colors to these different numbers, and you can apply this WL test. It's a colored distribution test, so that you can, it's at least an ad hoc test to determine if different graphs are isomorphic. And this is important because you can have these 2 graphs representing a molecule, for example, where this molecule is not toxic, but this one would be toxic. And you want to be able to differentiate between those, or have your neural network, your graphical neural network, to be able to tell the difference. And so what we want to understand is we want to find equivariant functions so that we can respect node order within the graph. And then we exploit a message passing ability of the graphical neural networks, right? This node is getting messages from the blue node and the purple node. This node is getting messages that are passed from this purple node to the 2 yellow nodes. And we can exploit this message passing architecture and the color test, the WL test, to understand a lot of information, to discover a lot of information about the graph and about how the graph interacts. We also do things like look at which nodes are providing more valuable information in a graph attention network architecture. And we can rank different messages within the graph. And so I'm going to skip over a lot of the math because it gets really in depth when you're trying to account for all of those things. But at the end of the day, we're able to account for all those things again within a Lyapunov-based architecture and have that stability analysis dictate to us adaptation laws for the graphical neural network. So we did a simulation where we had 6 agents. Only 3 of the agents were connected to a target. So that means that 3 agents couldn't see the target, but we wanted all 6 agents to track the target. And so these 3 agents that weren't able to see the target were able to exploit the graphical connections within the architecture to be able to follow the target because of the message passing that's happening among the different agents. So the target that we're tracking has some dynamics that we just made up. And then each of the agents in the graph has some, the ith agent in a neighborhood has some different interconnections. And we used a cyclic graph to represent this architecture. And you can see that originally there was a distribution of the nodes. The nodes all came together and they reached consensus with the target node, and they're able to follow the target node. We did a comparison with deep neural networks, graphical neural networks, and graphical neural networks with an attention neural network, with an attention mechanism within the graph neural network. And what we were able to show is that the graph attention network combined with the graphical neural network gave the overall best results in tracking the unknown target. And so to wrap up, what we were able to show is that, or just, in conclusion, uncertainty is inherent in all systems. And we want to be able to learn about this uncertainty in real time while we're executing the task. We don't want to, it's less desirable to try and collect some data if that data is available and run numerical optimizations on that data to converge, which doesn't give us a lot of verifiable information. And then it's less desirable to then lock in those weights and just implement that in an open loop manner. It would be more desirable to continue to do real-time learning during the task execution. And so that was one of the outcomes from this result. And it's exciting, and there's all kinds of future work to be done. Again, we haven't published our results on developing this work for transformers. Even when our emerging result comes out, there'll be much more to do there. There's many dissertations to be written on using graph neural networks for different applications, designing different adaptation laws. The CAN architectures, I think these didn't exist, 4 or 5 years ago. They're just emerging in the machine intelligence community. It's an opportunity, like I said, for us to have more interpretability about the learning. And so this is also a wide open architecture and an area of adaptive control to explore. Likewise, as we're using these new adaptation tools, I think there's lots of opportunities, and people internationally are looking at ways to do bounded learning or safe learning. And what I was able to show you today is that we're designing these analytical update laws using these analysis-driven methods from Lyapunov-based analysis methods. But there are other analysis methods. Contraction theory is an example, or embedding all this stuff within control barrier functions and using quadratic programs maybe to adjust the adaptation laws. There are lots of different different avenues to explore in these different deep learning architectures and using deep learning, but in ways that we have some sense of the stability and performance and robustness of the learning architectures, and can implement them in real time. So with that, I'll stop and just want to acknowledge my group of students that are working on these kinds of things, and very much appreciate everything I presented today was really an output from their creativity and hard work. If anyone would like to read more about some of the stuff that I showed today, this link is to my webpage, and all of our journal papers are there for you to download if you would like to read them or explore more. And with that, just thank you for the invitation to give a presentation today.
Thank you, Warren, Dixon, for a very informative presentation. And your presentation has driven me 20 years back when I was doing my master's. And the similar kind of things I was doing, but that was the fuzzy logic as a universal approximator. And there I was trying to design, I tried to design adaptive control methods. So I got motivated from your talk to I should revisit my work and see that how I can use your work for revisiting and giving a new dimension for my that work. So thank you for this informative talk. And we have been joined by Professor Mihila Albu. And let me introduce to you also so that you will be leaving. And she has joined. So she is a professor in the University of Bucharest, Romania. And Devanjan, you can introduce to the new speaker so that she can also take over.
Sir, Advika is here. Okay, Devanjan. Advika or Devanjan, whosoever is here, they can introduce.
Yes.
Yeah. Thank you, Dr. Dixon, for that enlightening session.
Thank you.
Our second speaker is Professor Mihila Albu, Professor of Electrical Engineering at Polytechnica University, Bucharest, Romania. A leading researcher in active distribution grids, DC microgrids, synchronized measurements, and power quality. Her work has influenced both academia and industry. She will deliver her talk on measurements and models applied to emerging power systems. Ma'am, we invite you.
Good evening, ma'am.
You have to unmute yourself. Dr. Albu, you have to unmute.
Yeah,
Yes.
I did it, but not with enough force. So hello
Okay.
again. So happy to see you again. I'm really happy to to see you,
Yes.
and of course to feel the presence of those who are attending today the presentation. And I will try to yeah. I hope that now one can see the screen. And as you see, the presentation is about the emerging power systems, about measurements and models. And I would like to point out that the key word in everything here is measurements. Now, the second keyword, but is much closer to my soul, is power systems. And the bad word here is emerging, because I presented some of the ideas here for several years already, and the word emerging attached to the power system was always there. And I was sure that in maybe not 1 year, maybe in 2 years, this world will disappear. So we will still have, or will soon have, the power systems that have emerged. They are still emerging. It's incredible. And being said this, my presentation is somehow a plea for looking for the reason why we are still working on the emerging world, emerging style, and we don't have yet what we all want. Remember what happened in Spain, the recent blackout, what happened last week in Berlin, another severe blackout. So we all hope that we will live in modern industrial power systems, but still is a long way there. Now, my presentation is again a distinguished lecturer from the IEEE Instrumentation and Measurement Society. Very briefly, just to recall the logo of the society, that we have a lot of chapters, and most of the chapters are in region 10, which means that I should feel really like at home now in this conference and setup. There is a lot of support for the chapters, for the students, for the women instrumentation measurement. Of course, all this information you can find on the website. What I would have liked just to draw the attention on the big flagship conferences on instrumentation measurement is I2MTC, but also I would like to spend 10 seconds, maybe less, on the only conference, actually it's a workshop on measurements for power systems, and this is this IEEE MPS, which in less than 6 days will start in Bucharest, in Romania, hosted by, for the first time in Eastern Europe, hosted by my university. The publications, of course, we want to be known as authors of our work on instrumentation and measurements, and we have the transactions, the open journal. Other 4 seconds, please remember that after 1st of January, actually in around February, there are IMS student contests. You are invited to apply, and Best Dissertation Award and Graduate Fellowship and Faculty Course Development Awards, all dealing with some measurements applied to your work. Also standardization. Because you heard that I am from Polytechnica, University of Bucharest, for many years. Actually, I graduated from this university as well. The power system faculty now grew up like a baby, is already more than an old person, because my university celebrated already 200 years. You see there are a lot of students, faculties, and so on. But why I'm speaking? Because my group, but I should say my colleagues, in the group that we call Microdar Lab, we have been awarded with tough competitions, but this is not important. We work for several projects, and as you see, the one that are ongoing, they are on dealing with power and energy. For instance, Eclipse is energy consumption reduction based on open source reference framework. About Econ for Future, which is fiber-driven energy communities for the future. About Infuse information fusion of multi-vector real-time data streams for energy management in emerging power grids. And the most recent one that we coordinate is novel current control for climate neutral energy infrastructure. The others are also related with the same concept, and that is measurements we all consider reflect reality, and application control in power systems that is the reality, because we support the effect of that control. And we have this project, we have this work, or we pursue this work. Why? Because unfortunately, these two realities, our mind reality, our real reality, what is happening, they do not converge always. Or let's say they don't converge anymore. So we are looking from one side, and that is what is going wrong from the side of measurements. And we discovered that, well, it's not a big discovery, but what is going wrong is with our imagination on what is there in the power system. And those are the models. So I will skip the outline because you'll see on the flow. And don't be scared. I will not speak about this figure that I love for several years already, because as I told you, I imagine that this will be implemented. Still is we are on the way to the future power system. What I want to recall is that still we are in a kind of mess in using the electrical energy. I'm speaking only about electrical energy because we started to harvest the energy. We started to use power electronics. We started to use more and more the DC generation and use, so at direct voltage electricity. We discovered that is needed to develop new control schemes, and those should be based on the flexibility of at least one partner in this merging complex system. And that partner now, it seems that should be the user of electricity, and not, as it was so many years, the generation. In conclusion, we have to shift from energy towards power control, and seems very, very easy. Is not yet. And we have to acknowledge the effect of lower time constants of all the phenomena that we have to control. The only bright, the sunshine, if we can think like this into all this picture, comes from the availability of the signal processing very much and electronics developed area. And this means power hardware in the loop, software in the loop that is now available. So we should use it in order to solve the problem. So from all I said, the big problem is in control is here, that we need real-time measurements and accurate estimation of partners flexibility, load and generation flexibility. And real-time does not accept the definition that we used 10 years ago. So what is real-time? We have no idea, because we have not the measurements able to tell us what is real time, because measurements are already corrupted with the notion of real time from 10 years ago and more. And if this sounds a little bit philosophical, let's go beyond. We are not able to discriminate between steady state and dynamic operation, because in the school, in university, we have courses on steady state with some models, and we have courses with methods and everything beyond on dynamic. Well, now we don't know what to apply because we cannot discriminate. And let's continue to the mess that is behind this, and unfortunately is in the measurements area. Traditionally, because we loved for planning purposes and also for steady state control purposes, we love to assume steady state over several seconds, and seconds, this is well, for normal for countryside power system is in the range of 4 seconds, and this is already inherited by most of SCADA operation. So because of that, we operate with averages and with representation of signals as quantity variation in time, not with real signals, but with averages. And those averages are really historical in the form, or all converge in the form of the root mean square, as we see here, which actually shows us that we operate with filtered, very hard filtered information that is equivalent with a super lossy information compression. Would not be a problem if we would be alerted, if we would know that is a data compression and information compression. Okay, then we will try to solve or to address it, but is hidden into the models and into the way that measurements are organized, devised, the measurement equipment, and used. I will not describe what is here, actually, just to say that that we have our signal, let's say, is the voltage, or let's say a power, electrical power signal. Then we use the modern way of digital systems and measurements, and what we obtain at the output of the analog to digital converter, we don't transfer anymore, although we try with these new standards of sample values recently, but it's very, very low, acquiring the realm of power system engineers. And then we decimate. And this decimation, at a first glance, is presented as a triumph, because by decimation you reduce the associated uncertainty with each measured sample. So indeed, the uncertainty associated with the measurements is smaller, but because what we obtain, the message that we obtain at the output, is not representing what we wanted, which means the actual quantity, the distance from the message, this and the reality, which is captured by the distance from what we measure and the model of the reality, is increased. And this is a kind of estimation of the semantic noise, as we call it in the measurement framework. And we have to investigate if it is important or not. So actually what we have to do is to look into the physical system, in the part of the power system, and look if what we do with this averaging is increasing in an acceptable way this model uncertainty, these definitional uncertainties, or this estimate of the semantic noise. Now you say, okay, we don't care. These are only words. They are U from uncertainty. What is our problem? Well, our problem is that if we look to the power signal, I'm sorry, because I was I was alerted that I have to finish in about 10 minutes. So if we look to the power signal, here is just a power profile at a household, and this is obtained with 1 second reporting rate, which means every second we measure the power, which means the energy with smaller time constants, and what we see by averaging, if we would average what any energy meter is averaging, while what any engineer is already doing with his or her head by averaging the information on energy translated into mean of the power, and we can calculate the information loss, which is huge. It's about 100%. Depends on the power profile. So if you are scared that here the average is when the information loss when we use 1 hour average is 140%. For another type of power profile, here is with the using of washing machine, is maybe only 113% only. So then you can say maybe we are unlucky. Let's look to the larger space, and we have a lot of measurements for just a normal apartment in the countryside, and we established that well, this information loss is not negligible. So we started some projects. One of them is using the integration of data from the student buildings and also from a real household, complicated household in the countryside is the Green Mogo, as you see, and we integrate the data using adapted smart meters able to deliver every second the electric power, so the power profiles for load, for PV we install, and also we use sensors to see if we can relate some of the information with outside of the energy system data. And actually this was the aim of seeing how this averaging and information loss from the electrical part relates, influence the information which is without loss because has much lower time constants from the weather or from other type of activity. And this is just a presentation that is available also on several papers recently about the infrastructure diagram, how to take from the SMX. SMX is the part of the energy meter that is available to give us data integrated in an Orion context, and then in the database to integrate the data and compared with simulations. Here we did simulations in RTDS. It was not done in Polytechnica, but in Athens. Meanwhile, in Polytechnica, we grew a system based on Typhoon Hill. So the idea is how to compare the models that we use even in hardware in the loop or only software in the loop, and match the reality. The reality represented by measurements closer to the adapted to the time constant of the phenomena. If you ever want to use this data, they are available on the IEEE data port. It's 1 year residential smart meter energy time series, active power with 1 second reporting rate. And that it's either from a household or a student building. So you can play with them. What can you play? Well, we were thinking then how to communicate this variability. I showed already these power profiles and how to communicate. Oh, this is crazy on the student houses. Look, each floor is a different color with the power every second during 1 day. This is worse than another student house. How can we quantify this variability? And unfortunately, it was nothing out there. So we looked to the estimators, and here is a lot of work. And out of all those metrics that we use for estimating how good a estimation process is, we concentrated to two of them, the coefficient of determination and the coefficient of variation of root mean square error. So these two, but of course, after we looked in some of them. So what is the idea? The idea is that we have a model in mind. Unfortunately, not only we have the model, but also the measurement equipment provider. And there are some samples acquired from the measurements. And then the measurement equipment is fitting all those measurements, all those dots that we see here in red, to the model that we communicate, that is the star of the reality there, which means for voltage, that's sinusoidal wave, which means that the model would be completely described by the RMS frequency and the phase. Based on the inspirational work of Harold Kirkham and Artis Ripnikis from 2016, we started to look into the goodness of fit applied of these samples, how good they are fitting the model that we have, and started to work on that, but not only with definition of goodness of fit, but also with the estimators and these operational indicators that I was announcing. Now here just some results, but they are not important. Important is the process and how we applied the idea to different different descriptors of phenomena, different quantities. So for the power profile variability, which we saw that it's of high importance, especially in smaller communities, energy communities, in order to plan and especially to operate such communities, we applied, but it's not the difficult part is how to select the time interval for calculating these indicators. So variability over 1 year, variability over 10 seconds, variability of over 2 hours, we have to select that based on the process and the history of previous measurements, and also how to select the model against which we make these measurements. And the model, of course, it's a subject of what is embedded in the existing measurement systems, and also what is embedded in our head when we devise the existing control systems. Here are selections of how to apply the goodness of fit, not only those metrics that I announced. For instance, if we select the model, the maximal power, and the model for a power delivery would be the nominal, the rated power at the connection point, then an ideal low voltage circuit at home, for instance, would be defined by the goodness of fit of about 12.7 decibel. And what is it above means that is better goodness of fit of this to this model. So application of this metrics can show a lot of information on the system that we study. For instance, applied for the power profile in a single user. So for a smaller community, we can see one value every day. Then we can find one value. So we stamp for 1 day usability of electrical power with the goodness of fit in order to compare and several users in a planning energy community. This is one line of work. I will not insist on other indicators, as I said, coefficient of variation of root mean square deviation, but the same idea I would only announce that was applied also on the frequency variability, because frequency might be a much more interesting quantity today when we strive for discriminating, as I said, between static and dynamic situations. And we were lucky to have data with high reporting rate, which is 50 frames per second from the PMUs installed in Romania. Lucky in the sense that we have data also from faults, so with high variability, not only quasi steady state system in all these 14 nodes. And we were looking to the variability of frequency. The measured frequency is here. We depicted only a few nodes. Then we selected several nodes and we tried to define the model. The model would be the average frequency over 1 second or over 10 seconds, as usually considered in the power quality, and then deriving the indicator of the frequency variability, as you see, R squared, so the coefficient of determination or coefficient of variation. And we can see very easily with such small computation that is announcing what is happening, frequency deviation, and we can calculate based on this the regions of frequency variability that is close to, let's call it, to the acceptable limits. Of course, we can do this with a power flow because we have data also with 50 frames per second reporting rate. For all these important lines, this actually shows the network 400 kV network in Romania, where we have the PMU installed. And we can see there are some lines that show high power flow variability in terms of coefficient of variation. And that allowed us, and this was one of the interesting results, to decouple or to identify from the whole region for different subregions, for the 400 kV network, where the rate of change of power, which is the variability index for each in each region, is different, which means that the consequences of an event might be different. So, because I don't think that I have more time, and I don't want to go over the planned schedule, I only want to say that all these measurements with high reporting rate, they have an enemy. I mean, they have a drawback. What to do with so many measurements, because we will be overloaded and will not be able to see the essential. We capture the essential with those flexibility indicators, but in the same time, we'll have too much data, and this is what power system engineer says. Well, it's better to be wrong than to be to die covered by data. And we explored this with other tools, much more related with the previous presentation, and it's about data analytics, with where we want to have we want to explore the energy profile forecasting, and using existing techniques, TS Fresh, and especially matrix profile, that you have, because you have the presentation with all these papers opening the area, just to say that in this way, with a lot of work based on data analytics, we can discover models that are a little bit closer to the reality, using high reporting rate measurements, which we already decided that are unavoidable, because otherwise, with low reporting rate measurements in dynamic systems, we have too high information loss. I will just skip these slides, announcing that another line of work was how can we predict the quality of the result of data analytics if we have either high reporting rate measurements, as we have here with 1 frame per second, so the power profile, or we have this lower reporting rate measurements, so only 4 frames per hour every 15 minutes, so averages, yeah. We know that is a high information loss, but we are curious what is happening into the matrix profile image if we lose or not information as we expected. And we see that actually the identification of the points of discords, so where the data sets are much more distant, is working fine for both of high reporting and low reporting rate measurements, which is actually the line of work that is opening now to see if we can reconcile these two issues related with data and measurements and models in power system. Here is my last slide. It's about how to detect the anomalies using the matrix profile, but also with data previously filtered with a Hampel filter in order to understand what is outlier and what not beyond the statistical approach. So thank you very much for paying attention, and I'm so sorry that I think that I was a few minutes late, but I am waiting for your questions.
Okay, so if there is any question from the audience, you can write into the chat. In meantime, let me thank you to Dr. Albu for joining. For us, it is we are moving towards the late evening. For you, I think that it is what is time currently?
For me, is only 20 minutes by 6 p.m., which
Okay,
is
okay.
just
So for you, it's the evening, the start of the evening. Yes.
yeah.
So one question that's thought, not the question coming in my mind, that what is the role of sampling rate when we are doing the analysis of frequency variability or the power variability? What is the role of sampling rate?
The sampling rate has a big role when we think to the maximal error and uncertainty associated with the measurement equipment. So the PMUs now, the most modern algorithms that are used by the phasor measurement units, which are still the best measurement device for frequency. So the sampling rate is about 50 kilohertz. Now it's at least for those models in compact Rio formation instruments. So beyond the 10 kilohertz, but that sampling rate is influencing only the error of the data that is given by the phasor measurement unit. From that on, so suppose that we reach below 0.1% total vector error and also very good low frequency error. From that point, the idea is what to do with the measurement. Because if we use the measurement every 20 milliseconds, how it is coming from the PMU, that is fine. The issue is what if we consider there are too many measurements and we start averaging or we start picking from time to time, so decimation, then is starting the problem. That the distance from the model and reality, so the data and the reality is growing. So what I would say is that put the sampling frequency as high as possible as to meet the requirement of the measurement equipment, and then and the requirement should be put by the power engineer, of course, and then the don't use in a wrong manner the jewelry, which is the information given by that measurement equipment. So this is the message. Yeah.
Thank you. Thank you for your wise comment. And there is a one personal note I want to mention that you were in India, I think that in 2015 or 2017. I forget to the year that when you were here with us in RDCAPE. So we will love to host you again, and whenever you have the time permits, please visit again to Amity University. Thank you.
Thank you very much. I really can't wait. Yeah, it was a really, really lovely time and very fruitful exchange. Yeah, I hope that will be in the future as well.
Thank you.
Thank you.
Devanjan, you can
Yes, sir.
proceed further.
The measure of intelligence is the ability to change. Thank you very much, Professor Dr. Albu.
Our final keynote speaker this evening is Dr. Shahroz Anjum, power generation engineer at Alliant Energy, Iowa, USA. With strong expertise in solar power systems, photovoltaic optimization, and renewable energy, she blends academic and industry knowledge. She will present on integration of renewable energy sources with battery energy storage systems.
Good morning, everyone. Am I audible to all of you?
Yes, you are
So
audible.
let's.
Morning.
Okay, sir. Good morning, sir. How are you?
Morning. Fine, all fine.
So yes, sir. Actually, yeah, I'll just going to start my presentation. It's 10 a.m. over here.
Okay.
So yeah, that's
We
the right
know
time
that,
for me.
yes, for you right time, but you have to do a lot of things, I understand. So you can take cut short if you want to do that, right?
Sure, sir. I will do my best.
Okay.
Yep. So I'm going to share my screen. So can you see my screen now, everyone?
Not
Oh, sorry.
yet.
Because just a second. Oh. Okay. Now, hopefully you can
Yes,
see
it's
my screen.
coming.
Okay. Yeah. So, yeah. So good morning, everyone. I'm Shehos. Just a sec. Yeah. So good morning, everyone. I'm Shehos, and my presentation is based on sustainable digital infrastructure, integrating renewable energy and battery storage system with data center. And let's start the introductory part of my work. So as we know that fossil fuel are the primary source of the energy in today's world, energy is generated by the burning of fossil fuel, produce emissions such as carbon dioxide, and that further rises the environmental temperature because of the greenhouse effect. And as we know also that fossil fuel are limited in the environment and we cannot rely on forever. So we have to switch on the non-conventional energy sources like solar, wind, green hydrogen, hydro, tidal, biofuel. And because at this time, data center is a upcoming future for the entire world, and we need more energy. And if we are using fossil fuel for that, definitely it will harmful to the environment. And we also in this current status, we can see that floods are coming, going on, a lot of things, a lot of challenges are coming on the entire world. So we have to switch on the non-conventional energy sources. So non-conventional energy sources like say, solar, wind, and battery storage system, because it is more like stable solution for the renewable stuff. And so let's talk about the data center. What is data center? So a data center is basically the home for all critical IT equipment. It includes server, storage system, networking gear, and all things that keep data flowing. And think of it as a backbone that support cloud service application and even things like streaming. So the main purpose is to store, process, or distribute data securely and efficiently. So in short, we can say that whenever we use the internet for the big task, somewhere the data center is doing the heavy lifting. So why it is important, why data center is important? So if you check the email, so whenever we log in the Gmail, Outlook, or any other email services, the data is actually being stored and managed in the data center. So the inbox we see on the screen is really just pulling information from those server. Second is stream a video, like when you stream a YouTube or Netflix or video files are delivered to us through the data center. They make sure that we get fast, high quality playback without buffering. Third is a use cloud storage. So service like Google Drive, OneDrive, or Dropbox all depends on the data center. That's where our file are actually stored, and so we can access them anytime, anywhere. And fourth is a make online purchases, like e-commerce platform like Amazon, Flipkart, other that is also required the data center, from browsing a product to payment and order tracking. It's also powered by data center. Then fifth is, as you know, that AI tools, even AI tools like chatbot or language model run powerful server inside that data center. They process huge amount of data in real time and give us answers quickly. So this is the basic structure of data center, like cooling units is required, and server is there, UPS system, backup generator. So these are the basic structures. Cameras are there. So these are the key components. So basically this is the key components of data center. Let me, okay. Yeah. So these are the key components of the data center. Server, storage system, networking equipment, cooling system, and power supply and backups. It's not moving. Okay. Yeah. So what is server? If I'm talking about the server, so in general, server are basically the workhorse for the data center. They handle the heavy tasks, processing data, running application, and managing all kind of services that we can rely on. So type of server is the three type, basically rack type server, blade type server, and tower server. So rack type server, what is that? So rack type server are designed to fit into the standardized rack. They save space and easy to organize, and which make them very popular for the modern data center. Think of them, we can think of them as a stacked shelf of the computer. Then second is a blade server. Blade server are even more compact. They are thin modular server that slides into the chassis, and the design allow high density, meaning you can fit more computing power into the less space. So basically they are great when efficiency and scalability are the key. Third is a tower server. That tower server look like a regular desktop PC, and they often use in a small business or office that don't need a full data center setup. They are very simple to manage, and but they take more space as compared to rack and blade data center. Yeah. And storage system, if I'm talking about, so what is the storage system? The key purpose is to make sure information can be stored in a different format and retrieve quickly whenever it is required. So three type of storage system were there in DAS system. That is a DAS, second is a NAS, and third is a SAN. So DAS is a direct attached storage. What is that? So this is the simplest form of the storage. It directly connect to one computer or server. Think of an external hard drive or USB drive that basically a DAS. It is fast for one machine, but since there is no network, only host can use that data. Second is a network attached storage. Like now NAS is connected to the local network and can be accessed by multiple users. It provide fee level access, so it's great for the things like shared folder in the office. If you ever use a shared drive at work, that is a next action. And third one is a SAN, storage area network. So SAN is more advanced and it use a dedicated high-speed network, often with fiber channels. So instead of file level, it provide block level access, making it ideal to large databases and enterprises and centers. And it designed for high performance and reliability in a big organization, basically. And this is the basic structure of the server and how these are connected to the SAN, NAS, and DAS system. And networking equipment, what is that? So if in short, networking equipment is what connect everything inside the data center. So it helps server and storage talk to each other and also connect the data center to the outside world. Without networking, all parts would be separate and not able to share the data. And type of networking stuff is switches, router, and firewalls. So first we will talk about the switches. So switches link device inside the same network, like server talking to each other. They send data only when it is need to go, which keep the things fast and avoid traffic. So you can think of them as a traffic controller inside the data center. And second is a router. Router connect different network together, like linking the data center to the internet. They choose the best path for the data to travel. It's like a GPS that guides information to the right place. And third is a firewall. So firewall keeps the network safe by checking what data come and go, basically. So they block everything suspicious or harmful, and you can think of them as a security guard of the data center. And if I'm talking about the cooling stuff, what type of cooling that we are using for the data center. So cooling system is really very important for the data center. They keep temperature and humidity at the safe level so that server don't overheat. And without cooling, the equipment could fail, even shut down. So we need cooling for that. So type of cooling is a raised floor setup. In the setup, the server racks sit on the rise floor. So there's an empty space under the floor called floor void, and cold air flow this space and rise up to keep the server cool. It's one of the most common method used in a data center. Then other cooling system is a CRAC unit, computer room air conditioning, and computer room air handler. So what is computer room air conditioning? So CRAC unit work with the big having big air conditioners. They blow air into the room and pull out hot air. This helps to keep the entire room safe at a safe temperature. Then other is a computer room air handler, that CRAH unit use a chilled water and fans inside the cool air, and they are usually more efficient than CRAC units. That's why we often use in a larger data center where the cooling demand is very high. And the last one is a in-row cooling. So in-row cooling is another method of the data center. This is called, basically it's called in-row cooling. Here the cooling units are placed right between the server. This means that cool air is delivered much more closer to the heat source, and because the cooling happened right where it is needed, it save energy and make cooling more efficient. And power management system. Power system in a data center makes sure that all equipment get steady and reliable electricity. They prevent downtime and keep things running even if if there's a power problem. So types are uninterrupted power supply, UPS, power distribution unit, rectifier, and generator. So let's talk about the UPS. UPS unit is like a backup battery. If the main power goes out, they keep server running for the short time until the backup power is start. And second is a power distribution unit. So PDU distribute electricity from the main power source to all server and the equipment. And think of them like a power strip in the data center, but on a larger scale. And third one is a rectifier. So rectifier convert AC power to DC power, which many data center device needed, and this makes sure that equipment get right type of electricity. And the last one is a generator. Generator provide long-term backup power during the outage, and they usually run on fuel and keep the data center working until normal power is restored. This is the basic structure of rack, or where all the server are inside that rack. And security system is a access control system, surveillance cameras were there, and environmental monitoring system like temperature and humid sensors are inside that data center, and smoke detector are also there inside that data center. So basically, like in past, we use the CPU, because we don't need to store much amount of data. But now in current state, like lot of big giant data centers are over the entire world. We need to create that, because and it consume megawatts of power. And in place of CPU, they use GPU, and GPU required more cooling as compared to the CPU. So type of data center. So these are the various type of data center. That is the managed data center, enterprise data center, co-location data center, cloud data center, edge data center, and hyperscale data center. And they are using for different purpose. Like first of all, I will talk about the managed data center. So that is used for the medium to large business. Less maintenance or no maintenance is required, and provider handles updates. And then second is a enterprise data center owned by the company, large global company. Basically, this is best for that. And third is a co-location, that is medium to large business. It's good for that, rented from the provider. And cloud data center, any size of the business. And edge data center is small to medium business. Best, it's best, this data center is best for small to medium size business. And then the last one is a hyperscale, that big enterprise cloud business. So these are the different types of data center. So it depends like which type of data center we required. According to that, we need to have it. So design and architecture, how the data center are designed. So according to that, basically, we have four kind of tiers. Like tier 1 is a basic structure. That key feature is a single path for the power cooling. Redundant components are not required. Maintenance required. For whenever we need to maintain the system, we need to shut down the whole system. And annual downtime is pretty high, that is 28.8 hours. So for a small business with low uptime needed, for that we use tier 1 data center. Then tier 2 are the redundant component, like single path plus redundant component, partial maintenance without shutdown. And annual downtime is pretty high, that's 22 hours. And cost conscious business need moderate reliability. Tier 3 is a concurrent maintainability, multiple power and cooling path, and +1 redundancy is required, 1.6 hour annual downtime, and medium sized business need high availability. This type of data center. And that last one is a type 4. And type 4 basically, like for the hospital and for other stuff, we need a low downtime. We are using this type of data center, and it is completely redundant system. So managing heat and power in data center. So our modern data center cooling strategy is crucial for both managing heat and improving energy efficiency. High performance computing, AI, and other demanding applications are increasing heat density, push data center to mix air and liquid cooling method. Basically, we are using two type of method. I mean, the combination of both air plus liquid cooling method for that. So let's talk about that Google data center, aiming to understand how customer data is protected inside that Google data center. So Google data center has basically 6 layers. Layer 1, that is the property boundary. The first layer of this is the first layer of security, is a property boundary. And this is usually include fencing and sign that mark the outer edge of the data center, and it set a clear limit for where the secure area is begin. Second is a secure perimeter. The second layer is a stronger and more secure perimeter. It includes smart fans that can detect movement or any contacts. Third is any content, and overlapping camera, like 24/7 guard patrol, make sure that area is always being watched, and thermal camera help even at night, and crest barriers stop vehicles from forcing entry. So these are the layer 1 and layer 2. And the layer 3 is basically building access. That's the third layer, focuses on entering the building itself. Access required a badge and sometimes iris scanning. Only one person can enter at a time through the secure door. So no tailgating is allowed. And this ensure that identify this ensure that identity is verified, and not just for the position of the card. So basically, a proper identify the person properly. And the last is the Security Operations Center, SOC, that the fourth layer is the SOC, which monitor everything 24/7. It gather data from door, camera, badge readers, and biometric scanner. And the SOC is the center hub that detect unusual activity and responds quickly. And fifth layer is the data center floor. The fifth layer is the actual data center floor where the server live. Access is only for essential person like technician and engineer. So at Google, for example, less than 1% employee can ever enter in this area. And the sixth layer is the disk eraser and destruction. So sixth layer deal with the retired drive. So drive enter through the secure two-way locker. Only authorized technician can handle them, and they can discard and physically destroy the whole stuff. And this is also called the crusher room. So let's talk about the challenges. So challenges in data center is currently because it required 2 to 3% of the global electricity. And currently we are using fossil fuel to run that data center. So this is the biggest challenge. Third is need 24/7 uptime. That is also crucial. And growing demand of AI, clouds, and IoT also, it create a lot of workload on the data center. And renewable energy integration with the data center. So what are the benefits if I'm integrating the renewable energy with the data center? So low carbon emission, long-term energy cost saving, positive corporate sustainability image, and challenges are because the system like renewable energy is variable in nature. So that's the biggest challenge. So how we can overcome that challenge, like role of battery in the storage system. So store and renewable energy in peak demand and outage, enable load shifting and grid support, improve reliability and uptime, and reduce dependency on the diesel backup. So that's why it's a better solution to add the BESS with the data center. So what is battery storage system? So BESS store an electrical energy using batteries like lithium ion, enable energy supply when the generation is low or demand is high. Crucial for integrating renewable like solar and wind into grid. So help to balance the supply and demand and reduce the grid stress and increase the reliability of the system. So why BESS? Because it support transition. Like we can transition to renewable energy like solar, wind, and hydrogen, and also it address the instability from the intermittent sources and also reduce the carbon emissions. So BESS structure, if I'm talking about, first we have battery cell, and then lot of battery cell combined together and they create a pack. And with that pack, a lot of packs are combined together, and that packs are inside that container, large container, and it's like a soccer field kind of system. And also the best part is that we use that secondary life battery, like we can use the discarded electric vehicle batteries also. This is the basic structure for that system, battery storage system, that cells and battery system and BMS. So these are the, so yeah, these are the basic systems like HVAC, power conversion. This is power conversion system. This is cell, and that's the battery storage system, and power main control unit, and BMS, battery management system, is this one. And this is the complete rack. So this is called battery rack. And so yeah, these are the things that is also required. So how BESS work? So BESS has the basically battery module and inverter inside that battery module that convert a DC to AC, DC to AC, and when it is connected to the grid, also it can convert it AC to DC, and also BMS, that is the battery management system, is also there. And industry players for that, who are the players for battery storage system, is the full solution provider, the Tesla, and system integrator, that is the Siemens and Samsung battery system, and second life integrator, like they are using, we using automotive battery systems. Challenges are EMC, that is the electromagnetic compatibility issues from high power electronics, communication distance limitation within the container, that is the major issue, challenges that is inside the battery, and fire safety and temperature issues. And how we can overcome is safety system like fire detection, air conditioning integration, and external communication gateway. We can use it OPC, UA, MQTT, IEC 61850. So these are the things that we can resolve it. And these are the word data center, and we can see that in eastern places we can see that, yes, sorry, in west places the data we have plenty of data center, that's 2868, and in east side we have 360 near this much data center. And in future, the future of sustainable data center is hybrid model, that is renewable plus BESS plus smart grid, and AI driven energy optimization, predictive load management, carbon negative data center. We can do that, and a strategic role in achieving net zero emission goal. Thank you.
Thank you, Dr. Anjum, for such valuable insights. With this, we conclude our plenary session 3. If any of the faculty members have anything to say.
So anything anyone likes to ask, you can write in the chat so that we can have 2-3 minutes to take if there is any question. So I think that there is no question. So thank you, Dr. Saros, for giving your talk. Always it is very informative, and the presentation that you share, that always enrich us with new information. So again, the same thing. And thank you for joining this morning for you and evening for us. So again,
Thank you, sir, for
thanks.
Thank you, sir, for your invitation.
Thank you very
Yeah.
much.
Thank you, sir.
So I think that Devanjan, I think that we
Yes,
have
sir.
done. Suhail, you want to? Okay, so we have one alumni has joined, Mr. Sheikh, Dr. Sheikh Suhail. He is postdoctoral student, so he is appreciating your talk. So I thought that I should convey you, right?
Thank you so much, sir.
Thank you. So thank you
Thank
all
you.
for joining this informative talk session. We conducted 3 talks today in this session. That is, first one was Professor Warren Dixon. Second one was from Professor Mehila Albu, and then now next, just we had concluded the talk from Dr. Saroz Anjum. So we will be resuming again next morning from the plenary session. That will be 9:45. So looking forward to see you again there. Thank you very much.
Thank you, sir.
So IT team, thank you for your support, and you may please close this session.